Good day, viewers. My name is Darlington Okoka, and I welcome you to Delwit Electrical YouTube channel. So let's talk about one important aspect, which is the current divider rule. We've agreed that different currents flow through different resistors for circuits connected in parallel. So let's see how we can get individual currents across each circuit. This current divider rule helps us to easily calculate the current across each resistor. So let's go from our first principle, which is the Ohm's law. V is equals to IR. That's our equation 1. Then our R from our previous calculation is our R equivalent. For parallel circuit, 1 over R equivalent is equals to 1 over R1 plus 1 over R2 till the total number of resistors in the circuit. But most times, it is advisable that we use conductances, as I said previously, instead of resistance when using the current divider rule, except there are only 2 resistors in parallel. So if there are only 2 resistors in parallel, you can go ahead and use your equivalent resistors. So like I told you, R equivalent is equal to R1, R2 over R1 plus R2 for only 2 resistors. So in that case, we could substitute our V into our R equivalent in equation 4 from what we can see on the screen, equation 4. But in parallel circuit, voltage is constant. So if we use equation 3, we can get V is equal to I1 R1, which is equal to I2 R2. Therefore, our I1 will now be V over R1, our I2 will now be V over R2. Now, if we now put our V now, which is I1 R1, if we now put it into our equation 4, we will now see that V, which is I1 R1 above, we will have I1 R1 is equals to I in bracket R1 plus R2 R1, which is our R equivalent. So this is all this now. We also get our I2 R2. Our I2 R2 is equals to I in bracket R1 plus R2 over R1 plus R2, which is our equivalent resistor. So if we divide both sides by R1, we'll now get our I1 in equation 5 is equals to I in bracket R2 over R1 plus R2. Then similarly too, we also divide both sides by R2. We have I2 is equals to I in bracket R1 over R1 plus R2. So you can see that for circuit that have just 2 resistors, we would see that the I1 for resistor 1 is I in bracket R2 over R1 plus R2. Get that? We are looking for I1, but the value up is R2, not R1. So it's inverse. So the total current shared in a parallel circuit by the resistors is in inverse proportion to their resistance. This is known as the principle of current division. So when we are talking about the principle of current division, is in inverse proportion. So for 2 resistors, I1 is equal to I in bracket R2 over R1 plus R2. If we are looking for I2 will be equal to I in bracket R1 over R1 plus R2. So don't confuse. When you are looking for I1, R2 will be up. When you are looking for I2, R1 will be up. But take note, that is if it's only 2 resistors. But if there are more than 2 resistors in parallel, you cannot use that formula. If there are more than 2 resistors in parallel, you cannot use that formula. What you have to do is you convert all the resistors to conductances. Like I said, conductance is inverse of your resistors. From the equation you can see, our G is equals to 1 over R, which is an inductor. So if we divide both the numerator and the denominator of equation 5, if we divide both the numerator and denominator of equation 5 by R1, R2, we shall get, if we divide it by R1, R2, we'll get I1 is equal to I over R2 plus R1 plus R2, which is equal to R2 over R1, R2 over R1 over R1, R2 plus R2 over R1, R2. When we divide that, we have I is equal to 1 over R1 over 1 over R2 plus 1 over R3. Therefore, I1 is equal to G1 over G1 plus G2 in bracket I. Then I2 similarly will be equal to G2 over G1 plus G2I. Thus, you can now see that if we are using conductors, it's very easy to conclude that when we are looking for the nth conductor, we'll have our In is equal to Gn over G1 plus G2 plus G3 plus to infinity Gn times I. That will give us our current across that number of conductor. Let's consider two empty cases. On the screen, you would see a circuit where we assume that the resistor R2 is equal to 0. Since the resistor is equal to 0, that means we have shunted the circuit. Therefore, equation 5 and 6 will now be I1 will now be equal to 0 over R1 plus 0 I, which is equal to 0. So I1, current flowing through I1 is 0. For I2, we have R1 over R1 plus 0 because R2 is 0 now. So in that case, we have R1 over R1 I. That means the total number of current in the circuit now will now flow through the position of R2. So that is also gives you the instance of earthing system where you have the lowest resistor. That is where current tends to flow through. So all the entire current in the circuit will now flow through R2. So let's assume the second one now. If we assume from this circuit seen now, we have an open circuit on R2. That means R2 tends to infinity. So if we take the limit of equation 3 to tending to infinity, we now have our R equivalent is equal to R1 because there is no R2. R2 is to infinity. So from equation 4 now, we can have I1 R1 is equal to I in bracket R1 R2 over R1 plus R2. Since we have taken this to be to infinity, we will now have our I1 R1 is equal to I R1. If we divide R1 by R1, we have I1 is equal to I. So the entire current of I1 is the same as I. Now for I2, we now say that I2 R2 from equation 4, I2 R2 is equal to I in bracket R1 R2 over R1 plus R2. I2 R2 is equal to I in bracket R1. I guess you get it. So now our R2 now is equal to I R1 over R2 infinity. You can now say that our R2 tends to 0. So when there is an open circuit, you discover that the entire current flows through where the circuit is, through R1. And when there is a shunt circuit, the entire current flows through R2, which is the shunted part of the circuit. So I believe that we've been able to understand how we could calculate for your current that flows through a particular branch in a parallel connected circuit. So I know it has not been easy for you, but let's just solve a particular question and see if we are able to get the exact value of what it does. So on your screen now, you will see that we're going to find the equivalent resistance of the circuit shown below. On point A and point B, you can see 2 ohms, 3 ohms, 4 ohms, 6 ohms, 4 ohms, 5 ohms, 1 ohm, and 3 ohm. So you can, from this circuit now, it is usually advised to commence from the extreme away from the source, the side that is extreme away from the source. So hence, we are going to concentrate on the 4 ohms, the 5 ohms, and the 3 ohms. If you can see, the 4 ohms, 5 ohms, and 3 ohms, they are all connected in series. So our equivalent for the first section of the circuit is you add the 3 resistors together. When we add it, we have 4 plus 5 plus 3, we have 12 ohms. So this 12 ohms now, as you can see, we draw the circuit. You can see that this 12 ohms now is now in parallel with the 4 ohms. So we have reduced the circuit now to figure 2. Figure 2 is now equivalent to figure 1. You get it? So now, in figure 2, we have 4 ohms in parallel with 12 ohms. they've asked us to find the equivalent resistance. So we're going to reduce this circuit to where we can find the equivalent resistance. So for 4 ohms and 12 ohms in parallel, what would we do? I've told you initially that when two circuits are connected in parallel, you multiply the resistance and divide by the sum. So our R equivalent now is equals to 4 times 12 over 4 plus 12. That is 48 divided by 16. We have 3. So the circuit reduces further to our figure 3. Now, in our figure 3, we can now see that the 3 ohms now is now in series with our equivalent 3 ohms that we calculated. So if you look at it now, our R equivalent 3 now will now be 3 plus 3, which is equal to 6 ohms. Now, if we further reduce this circuit now to figure 4, our figure 4 now shows that this 6 ohms in parallel is now in parallel with our calculated R equivalent, 6 ohms. So like I also said now, to calculate our R equivalent for these two, it will now be 6 times 6 all over 6 plus 6. If you divide it, we have 3 ohms. So 3 ohms is the equivalent resistance for these two, 6 and 6. So the circuit now further reduces to figure 5. In our figure 5 now, these two that is in parallel, we reduce it to a series. So you can now see that your 2 ohms, your calculated 3 ohms, and your 1 ohms are now in series. So if you add them for R equivalent for series circuit, you have to add together. So you add 2 ohms plus 3 ohms plus 1 ohm. The equivalent resistor of the circuit is now 6 ohms. So I believe this is the simplest way you would have to resolve a circuit, reduce it to the barest minimum so as you can get the equivalent resistance. We've been able to combine both the series and the parallel aspect of the circuit. So if you didn't follow properly with this calculation, please try to listen to our resistance in series video and get to understand how the series calculation operates. Then come back to this video and you see that this calculation is quite easy. If you have any questions, feel free to comment on the comment box and be rest assured that I would attend to every question on the comment box. So please click on the subscription button and the notification icon to get notified on whenever new videos are being posted. Thank you for visiting Delwit Electrical YouTube channel.